So it's a pleasure to introduce this afternoon's speaker, Professor Euan Nisbet. He's from the Department of Earth Sciences in Royal Holloway, University of London. He did his degree and PhD in geology here in Cambridge, and after postdoctoral work in Oxford and Zurich, had faculty positions in Cambridge, Saskatchewan, before coming back to the UK as Foundation Professor of Earth Sciences at Royal Holloway in the University of London. His earlier work was on the early history of the Earth, that's the early geological history of the Earth. But more recently he's become interested in atmospheric greenhouse gases, and he leads a UK consortium on studying atmospheric greenhouse gases, especially methane. And he's also a trustee of Christians in Science. So Euan, it's a pleasure to welcome you this afternoon. And his talk's going to be on Our Fragile Planet, a Christian Perspective. Are we breaking the rainbow? Thank you.
Thank you very much. So, I was doing research in Canada in the early history, the Archean Shield, and I kept falling into beaver ponds, and bubbles came up. And I was also chairing the Canadian Lithosphere Committee, which had to deal with natural hazards like volcanoes and so on. And there were gas rigs falling over up in the Beaufort Sea. Why were they falling over? Well, they were drilling into stuff called methane hydrate. So it's way back in the 1980s. And the Governor General rather sillily gave me a couple of years to wander around the planet. And I went to New Zealand and realized we have problems. So, which is why I started working on this stuff. We started looking at those bubbles. So my theme here is that the rainbow is in trouble. The rainbow is something very important, and there are problems with it. This actually is where we get samples from in Spitsbergen. You could almost reach out and touch the North Pole, not quite. It's 400 meters above a little town called Ny-Ålesund. And it's the most marvelous place, and the air is not clean. That's our old air intake there. We don't use this one anymore, but as you can see, we're sniffing, and we can sniff a huge amount of air there. The graph in the corner is the one that's worrying us. That's the methane graph, and I don't need to say what the axes are. Okay, so I'm going to go to the rainbow. The rainbow is quite extraordinary. If you think about the planets, it's actually quite difficult to get a rainbow. You've got to have rain. You've got to have sun. You've got to have an atmosphere that lets the right sort of light through. Hard X-rays, the atmosphere's got to stop that. It's got to stop the hard ultraviolet and only let a little bit of the soft ultraviolet through. And it's got to have an open window for the visible spectrum, which is exactly what you see there. But then when you get to the infrared spectrum, well, there's rain. That's going to stop a lot of the infrared getting out. And so over the wide infrared spectrum, what comes in, the energy, has got to equal what goes out. Otherwise, things will either get hotter or colder, and the energy of the frequency of the radiation going out will change, and eventually you'll get a balance. But if you have too much rain, then you won't get rainbows anyway, but you won't let the heat out. If you have too little rain, too dry, you won't get rainbows. It's pretty special to just get that. And unfortunately, we've been poking holes in all of that. We're sort of breaking the rainbow in two different ways. One is that we're changing the frequency of the outgoing by warming up the planet. And secondly, we're actually blocking the ingoing with our air pollution. So I want to sort of explore just a few things about what does the rainbow mean, how we get here, and where we might be going. Oh, that's my house near Heathrow. You can't see the aeroplanes taking off. Okay. We live in a waterhole. This is a classical thing. First pointed out, I think, by a friend of mine, a chap called Preston Cloud, who was a geologist in the last century. Shows how old I am. He wrote a marvelous little book called Oasis in Space. We are the waterhole. Earth is there. in other words, we get all sorts of different waters. We get water rock at the poles. We get the wet stuff. We shouldn't really call it Earth, we should call it ocean. Whereas Mars has only got a couple hundred meters, and Venus had a couple of kilometers but lost it. We've got the wet stuff here. And then we've got it in the air as well, so that you can get rainbows. That's a very precarious place to be. Stable planet should be not near that waterhole. It should be one side or the other side. And if you go to the hot side, you get to be like Venus, and eventually you partition water into the high atmosphere, and radiation knocks the hydrogen out to space, so you dehydrate the planet. Or if you go to the cold side, you get to be like Mars, where basically water turns to rock. Okay, so this is actually a photo. Unfortunately, I wasn't there. I sent a. We have a project called MOYO, which is Methane Observations and Yearly Assessment, which NERC pays for. MOYO is actually where I grew up in southern Africa. It means breath or wind or spirit. In the South African national anthem, it means Holy Spirit. And we had a project called Zwamps, which was the Zambian swamps. And this is actually how the atmosphere works. Sun coming down, water comes up, water gets up to a few kilometers up, and then air expands, gets colder, and it drops down. And at about 10 kilometers or so, you have basically the cold trap. Water can't get above that. Only a little bit can get up. Either CH4 can go through and then oxidize and make water up there, or a little bit can go through even when it's minus 60 up there. So it's essentially a recycling system. This is also the great washing machine of the atmosphere, the intertropical convergence zone, which cleans the entire planet up effectively. And in around those clouds, you get very bright sunlight, and there's something called hydroxyl, just OH, water minus an H, and that's the policeman of the atmosphere, because that runs around and oxidizes anything nasty you can possibly imagine, and when it's oxidized, it rains out. It dissolves out, and off it goes. So this is the big washing machine that cleans the planet. And if we do something to the washing machine, you're in trouble. Well, that's what we do. I'm going to put some quotations on there, which some of you will be familiar with and some of you won't. But still, it's a puzzle. And we're actually challenged in the Bible, both in Job and Isaiah and lots of other places, to actually figure it out. These things here, who's measured the waters in the hollow of his hand, that's not just a contemptuous boast. That's a go and do it. Figure it out. That's a challenge. All those things in Job. You know, Job isn't saying, who's stretched the measuring line. It's your job. Go figure it. Challenges us. Okay. I lived up in Canadian prairies for 11 years, and part of my ancestry is northern Canadian. Well, Saskatchewan's not that far north. It's about the same. Saskatoon's about the same as London, but it's minus 40 pretty regularly in the wintertime, and you get these wonderful things, sundogs. It's a different form of rainbow. Because you get the two partners of the sun. Absolutely magnificent sight when you see them. And this is a particularly good one. But you'd see sundogs a lot of the time. And again, this is ice crystals. But it's a particular part of the rainbow that most people are not very familiar with. It's a fascinating little trinity. And when you see that in the morning, as you're walking off to a lecture, you think, yeah, maybe there's something in that. And on the opposite side is the antihelical point, the spire on the far side, which is right opposite. You think, oh, what's there? And that's the bad stuff, but never mind. Some of you may well have seen the Brocken Spectre. I have once. It was quite extraordinary, walking down a hill, sun behind me, rainbow in front, and there's your shadow on the cloud. It's a magnificent sight if you see it. There's an interesting story about it because one of my wife's family friends, Charles Frank, was in Germany in the late 1930s, and he was told to go and see the Brocken Spectre and buy a camera and take a photo. So he went up to Brocken, which is in Germany, and of course he bought a wonderful Leica, I've seen it, and took photographs of all the radar stations, and that's how the British got the frequencies. Anyway, so the Brocken Spectre is important because we are actually in the rainbow. Right. So let's get on to some science. This is my favorite classical statue. It's actually Roman, 2nd century AD. It's comes from Aratus's book Phenomena, which was written a couple of hundred BC. And basically this is Atlas or somebody holding the universe. And you can see that that's actually a star map. The constellations are on it. Constellations as of actually quite some way back, Babylonian time really. But you can see the lines of latitude and longitude. And my son-in-law, who's an orthopod, he's a surgeon who sort of cuts you up and does bones. He says, yeah, classic. You can see the structure, the deformation of the shoulders because of the enormous weight. But this is really, in some ways, our first great textbook of the natural world. It's poetry. Newton wouldn't have written in poems, but still, it's meticulous observation. He keeps on saying, if you don't believe me, go look. It's also the first really decent textbook of the weather. And if anyone goes to Naples, you can see the statue. It's huge. It's a magnificent statue. So, that's Aratus, Phenomena. We still use the term phenomena. Well, there was a guy who read this, who quotes it, and it's a sound citation to kill all sound citations. He put it in the Bible. This is St. Paul. He quotes Aratus straight out. And he's actually speaking to the court of the Areopagus in Athens. And why the Areopagus? Well, there's a lot going on there. If you read Aeschylus, that's where Apollo denies the resurrection and then is overruled by Athena. It's also where Sophocles has Oedipus go down and then says it's a great mystery. We don't know what's happened. Only the king of Athens knows the answer. He's not going to say. And it's also where Socrates was condemned. And Paul quotes Socrates, necessity was laid upon me, the word of God. Paul effectively quotes that in 1 Corinthians. It's also, the Areopagus, the constitution was laid down by Solon and Epimenides. And here's this marvelous verse from Epimenides. They fashioned a tomb for you, the holy and high one. The Cretans always liars, evil beasts, idle bellies. Which is Gödel's incompleteness theorem. It's essentially one of the most important things in all mathematics. But thou art not dead, forever thou art risen and alive, for in thee we live and move and have our being, which is, Paul quotes that twice. You know, to quote it twice in the Bible, he's got to think it's quite important. And actually the full quote was lost until the marvellous sisters who founded Westminster College went off and discovered it in the writings of Ishadad of Merv, of all people, who wrote it before the Mongols trashed Merv. In other words, there's history here. Science is important. Paul is quoting science. He's quoting maths. He's telling us, go and look. So let's look. Okay. The rainbow. Liquid water is very, very ancient. We know that. There's argument about exactly how old loose water on the surface of the planet is. Around about 4.5 billion years ago, we have the great splat, when a planet the size of Mars hits a planet the size of Venus, and lots of splat goes out, and the whole thing goes liquid, and then it all settles down, and some of the splat makes the moon, the rest of it falls back down, and after that, you get the oceans. So the oceans are pretty ancient, over 4 billion years ago. But of course the early Earth would have been pretty cool because the sun was pretty cool. So very likely ice covered. I can't resist showing you some pics of the rocks I work on. These are called komatiats, absolutely beautiful rocks. And these are actually 2.7 billion, but these things would have degassed, and some of them got little bubbles in them where you can actually see residual melt that would have degassed and produced water. So they're just very, very pretty rocks. And yeah, so the ocean's degassed. Once you've got degassed oceans, then things can happen. Life starts somewhere around 4 billion years ago, and that's the beginning of what we call the Archean Eon. Now, Archean comes from the second word of St. John's Gospel, en arche, in the beginning. So the Archeans from 4 billion years ago to 2.5 billion years ago. These are late Archean, and these are stromatolites. You can see they're in very shallow water evaporitic conditions. There are little mud cracks in them. All sorts of wonderful structures, and they're basically structures made by cyanobacteria, but not just cyanobacteria, consortia of bacteria and then microbes called archaea. Here's a cyanobacterium. Most people, their children have stuffed dogs and things or whatever. My daughter had a stuffed cyanobacterium. Quite why she went for that, I don't know, but she's a microbiologist now, so it sort of figures. And these are cyanobacteria. That's my daughter's hand, actually. She's now in the biochemistry department, so she's a bit bigger now. Cyanobacteria are extraordinary because the green chaps there are busy drawing down carbon dioxide and water and knocking off the oxygen from the water and dumping out this horrendous, nasty stuff called oxygen. You'd never get planning permission for it because it kills everybody else. It's really horrible stuff. And then what is left over is organic matter. But that's producing oxygen. In the middle is the heterocyst, which is splitting N2, which is a very, very anaerobic thing to do. It's a very difficult thing to do as well. Right next to all this oxygen getting released. And that's essentially the factory that makes the modern atmosphere. The modern atmosphere is obviously run by the plants and the animals. A plant is essentially a cyanobacterium in a spacesuit, along with some purple bacteria in the spacesuit. The animals, they've got lazy and started eating their next door neighbors. And they're essentially just purple bacteria in spacesuits. If you're a purple bacterium and you want to go to the moon, you just invent an animal, simple, and eat your colleagues. Now, the atmosphere, with the exception of argon, is a biological construction. Everything in the atmosphere is biologically made. And you can argue that by stabilizing water on the surface of the planet, that also helps control the argon emission. So you could say that essentially the whole atmosphere is a biological construction. We still don't know what controls it. We don't know why the pressure is 1 bar. We don't know why the oxygen's about 1/5 of it. There are plenty of theories. The whole network is immensely complicated. Don't look at the details. But this is a very, very simplified diagram showing what's going on. But controlling the air then controls the temperature, and the temperature then controls the stability of the ocean, which then allows all these processes to happen, which controls the temperature and then goes round and round. Immensely complex feedback loops. Jim Lovelock pointed out that the atmosphere is essentially a cybernetic system. It has feedback loops. His next door neighbor or near neighbor, William Golding, then said, "Why don't you call it Gaia?" Which Jim did, and then of course everyone dumped on him because it's metaphysics, it's not science, but it is a feedback loop, or an immensely complex set of feedback loops. And that has stabilized water, which has not happened on Venus. Okay, so let's look at what's going on now. How am I doing for time? The wet tropics, the washing machine, they're the heart of of the biosphere. And they happen in very surprising places. If you look at this, it's an absolutely pristine wetland, tropical wetland. It's actually right on the edge of the tropics. And though you don't see it, if you look very hard in the background, you might see there are just a few signs there. That's actually in Hong Kong, which is a human ant-heap. 20% of it. The other 80% is most marvelous wild countryside, which this is. It's micro wetlands. If you turn around, there's Shenzhen, which is 10 million people, just a few hundred meters away. But the atmosphere still continues. Okay, so this is the circulation of the atmosphere, very, very, very simplified. We're all familiar with this, the air rising where the sun is strongest in September and March over the equator, where it lags a little bit because it takes time for things to move up and down. And so as it rises, it drops the water. The dry air coming down at sort of 30 degrees, so you get the deserts there. And then the cold air coming from the poles interacting with that, and so you get precipitation at 50, 60 north, which is where we are. And of course those belts move up and down as the sun moves up and down with the seasons, which is a consequence of the great impact 4.5 billion years ago. And the system is spinning as well, which means you get equal distribution of temperature around the planet. You don't have a hot side and a cold side. Absolutely marvelously set up just for us. Okay, so let's go into the questions. Sorry, I've just been in Switzerland because John Wood, whom some of you will know, took us around CERN on Friday. I supposed to have one of the nicest notes I know, which is dandelion, but it's actually the air circulation of the planet. If you're rich enough to be able to have a 50-franc note, which is... when I was in Switzerland many, many years ago as a postdoc, I thought, oh, 50 francs, wow, they'll keep me going for a week. Okay. Maimonides, the wonderful Jewish philosopher, but dating back far, far back to Hillel and people, the old Jewish view of the laws of behavior, the law of Adam, the first great commandment is love God. But then come the laws of Noah, which is very, very specific about looking after all creation. And so in Jewish thinking, you get the laws from Adam to Noah. Don't worship idols, don't curse God, establish courts of justice. Don't commit murder and adultery, and don't steal. But then don't eat flesh torn from a living animal. Don't take the life from the system. And that's then repeated by the early Christians. They very specifically refer back to that. Don't take the life from the system. And it's the one command that they keep attention to. We're not, if you're Christian, you're not subject to the laws of Moses, and Israel means wrestling with God, but you are subject to these laws because they apply to everybody. And particularly the law of in what I'm talking about here, the law of not taking life, and that's symbolized by the rainbow. Okay, so what are we up to? We're trying to measure greenhouse gases around the world. If you measure in one place, Mauna Loa or South Pole, you get a sort of indication of what's going on. But to understand where the emissions are and where the sinks are and how it's moving from A to B, you have to measure a lot of places. And we have a collaborative network around the world, which is run by US NOAA, Ed Dukansky, who's responsible for quite a lot of our slides. And then various people contribute. And this is our little network, the bigger dots here. And what we're trying to do is measure in these places and see how the air moves. You essentially run the weather forecast backwards. And so you have a series of measurements of carbon dioxide or methane or whatever it is in your place. You run the wind backwards to where it last touched ground. And I'm not a modeler, but I have an awful lot of modeling friends. And what they do is these monstrous Bayesian inversions. And from that, they can calculate the sources. And if you're lucky, the sinks as well. And of course, the budgets have to add up. So we have the equator inter-Atlantic north-south measurement. It's called after a very early Cambridge Arctic scientist, Euan, who sailed up into Spitsbergen, where we measure. And in the 1780s or thereabouts, I can't remember. Maybe it was earlier than that. I think he was on the same trip that, don't quote me on this, that Nelson was on when the polar bear almost ate Nelson. Didn't quite. And Napoleon would have loved that polar bear, but Nelson escaped. He was about 14 at the time or so. Anyway, Euan was also, although he died before it happened, very significantly responsible for the settlement of Ascension Island, which it was originally the base to guard Napoleon escaping from St. Helena, but then it became the main base for the war against slavery. And it was the Royal Navy's, one of the Royal Navy's biggest bases. For quite a while, it had a quarter of the Navy parked there. And they were patrolling the Atlantic, trying to catch the slave ships for, 80, 90 years or so. Okay, so that's what we're trying to do. And we measure in lots of different places. Over there is our measurement point in Spitsbergen. This is actually Jungfraujoch. We're not actually sampling there, but the Swiss are obviously, and the what's called the A-gauge network, which looks particularly at chlorofluorocarbons, they're working there. And some of you have probably been up to Jungfrau. When you get up into that Sphinx up on top, it's a marvellous sight. Now, it's part of the A-gauge network, and that very recently, Matt Rigby's work in Bristol has shown, for example, that China is emitting chlorofluorocarbons. You run backwards from where you measure, and then you can find out where the source is. So these networks are very important, and they're all staggering along on absolute minimum budget. So what have we got? Well, you don't need to know where those are. You can probably see those plots. The left-hand one is methane at various different places. It's Alert, Zeppelin, Spitsbergen, Alert's Northern Canada, Spitsbergen, Ascension, which is our place in South Pole, and that's a mixture of NOAA's data primarily and our own data. And on the other side is the carbon isotope, isotopic ratio of carbon-12 to carbon-13 in the methane. And I think you can see the trend. It's getting lighter. It's going downhill. That means that there's more biological methane in the total. So methane is going up, but the fraction that's biological is increasing, and the fraction that's fossil fuel is decreasing. Or there's a change going on in the sink, which is the hydroxyl. We're having this big discussion at the moment. We don't know which the answer is. Could be both. If the sink is getting less, then that's really bad news for air pollution. If the biology is pumping out more methane, which is also quite likely, then that tells you that the tropics are really changing. If you look at the latitudinal distribution, not there, it's primarily happening in the tropics. Now, it's just about Ascension Day on Thursday, so I'll bring you just an example of what we're doing on Ascension Island, which is a most marvellous place, unfortunately almost inaccessible now because the runway got broken. And here in Ascension, you have the low air, the southeast trades, it's come up really from the Southern Ocean, the trade wind inversion, and then the free troposphere above. And it shows you the partitioning of the atmosphere. And what we have all together is this problem. This is global temperature, Stefan Rahmsdorf's paper a year or two ago, where you can essentially see that somewhere around the end of the First World War, you start getting this climb. This extraordinary year, 1940, where things got really hot, which of course, Second World War, it was apparently a glorious summer here. We shouldn't generalize from Britain to the rest of the world. Britain actually has a fairly unusual climate. If you want to be in a place with, that's going to be relatively secure from global warming, Britain's a pretty good place to choose. Okay, we've got sea level problems, but apart from that, it's surrounded by ocean. It's relatively gentle, and the North Atlantic circulation is declining. So it's a good place to be, Britain or New Zealand or the Falkland Islands. And then in the last couple of decades, or since 1975, we've had this really strong warming. And then just in the last few years, since 2014, we've had something really extraordinary going on. So that's in the warming. Okay, we all know what's going on. My grandfather's uncle got stuck in there in the 1850s. He was looking for Sir John Franklin, and they actually, eventually, they had to abandon ship. He got court-martialed by his captain. He was a lieutenant, because he refused to abandon ship, and Captain Belcher said, "You must." And so he got arrested and came back under arrest. And eventually they exonerated him, and they exonerated the captain for losing his ship. And the ship sailed out the next year, and the US Congress, who were enemy power, they grabbed it. And what would an enemy do with an enemy ship of war? They fixed it up and they gave it back to Queen Victoria. And she was so astonished that was the start of the Anglo-American alliance. So it's called the Resolute. And at the end, when they broke up the Resolute many years later, Queen Victoria got out her saw and her plane and all the rest of it and her screwdrivers, and she made these two beautiful desks, which some of you have seen a really bad movie about them. One of them, I think, is in Buckingham Palace, and the other one has Mr. Trump on top of it. It's the desk in the Oval Office. So the Resolute desk. Yeah. So it comes out of the Arctic. Because they couldn't get through. They wanted to go to China, the short route. Now you can go through pretty much any year in September. That's the last September. You can, most years you can go through either side pretty much. It's astonishing. What's happening now in the Arctic is what was predicted about 10, 15 years ago to be happening at the end of this century. It's happening now. Right, I make marmalade. And at the end of making marmalade, you've got all the oranges boiled up, and then you put the sugar in. And then you turn on the heat. And yeah, the Arctic's in trouble. And as a Canadian Zimbabwean, I'm concerned about the Arctic. It matters to me. It is in a lot of trouble because it's warming up faster and more than the rest of the world. But the Arctic's a very small part of the world. The tropics are the really big factory. Now there the warming is much less, but in terms of its importance in the global system, much, much bigger. Though I shouldn't downplay the Arctic. If you lose the sort of, imagine you're totally bald and shiny, and then suddenly you grow a big head of hair. That changes the whole heat balance of your head. Likewise with the Arctic. We're now absorbing far more heat in the Arctic in summer. And that changes climate way down to southern Africa. It moves the jet streams. Okay, now that's climate. Well, how about composition of the air? I actually took this photo in 2003. Some of you will remember it was a very, very hot year. And this is on the Senjas Pass in Switzerland at about 2,600 meters or so. And you can just see the air pollution over Europe. That's actually a Swiss Army facility there. It's one of the most marvelous facilities I can think of. You can sit there and contemplate the universe. And we saw a little Swiss Army soldier come out and sit upon there. I was very envious of the guy. And it all falls down, which is pretty much what we're doing. We're dumping everything out. The air is basically our toilet. And occasionally the wind comes along and flushes the toilet. In London, 4 o'clock in the afternoon, you can see the trees fluttering and they get the overturn. And basically you flush the toilet upwards and it goes off and bothers the French or the Germans or somebody. So we have turned the air into our toilet. This is Hong Kong. Now Hong Kong's quite a clean city. But of course it's got an exceptionally dirty neighbour. And if you look at the people in Hong Kong, they're walking around wearing face masks. Part of that's because of the SARS scare some years ago, but a lot of it's air pollution. doesn't really work. Even here in Cambridge, I've noticed quite a lot of the Chinese tourists are wearing face masks, scared of breathing the air. What does that tell you? It's our own planet. We're not living on Mars. I was in Beijing in November the 19th, 2010, and the US Embassy had put a measurement of PM 2.5, particulate matter, on the roof. And it was the only honest measurement in the whole of North China, probably. And clearly whoever had programmed this thing had, you have various scales. When it's in the US EPA units, when it's 0 to 100 or something, it's quite good. When it's 100 to 200, it's not so good. When it's 200 to 300, it's distinctly bad. And when it's 300 to 400, it is awful. When it's 400 to 500, just go away and go back to bed and pull over the blankets. And when it's above 500, there was no name. It was so awful. And so obviously the guy programming it, and this is my hypothesis, I had never seen it confirmed, just he had to have something in there, so he just put crazy bad. And yeah, the instrument tweeted that the air quality was crazy bad, which may have been the start of a modern environmental concern in China. Because, of course, it did hit the headlines, it got into the New York Times, and it actually got tweeted around China too. And I came back and got hauled up on Bloomberg TV in Hong Kong the next day. Was it really bad? Yes. There's a photograph. Absolutely awful. It's now much worse, and Delhi, of course, is far worse than that. Well, they've been trying in Beijing to reduce it by just exporting to the countryside. Okay. So we have these enormous problems. In particular, I'm working on methane. Methane has lots of sources. Really big ones are the tropical wetlands. It's about 550, 600 million tons a year is emitted. Tropical wetlands, 150 to 200 million tons. Gas leaks and coal emissions, 100 to 150. Biomass burning, about another 50. Cows, agriculture, a couple of 100 million. These are the sources of methane. And we've been trying to figure out just what it's doing. Now, methane in itself is a major greenhouse gas, but it also has impact on other species in the atmosphere. So the net impact of methane is about half that of CO2, roughly, depending on how you count it. And so it's a very major greenhouse gas. And we tend to ignore it. We just think of carbon dioxide. This is what we call the flying carpet, made by my friend Ed Dukakensky and Noah. Along the axis along the bottom is the time. This is the last 10 years, 12 years. Vertical axis is the amount of methane. And then South Pole at the near end in the 3D diagram, and North Pole at the far end, if you're seeing it that way. And you can see how most of the strong production of methane is in the northern hemisphere. It then blows southwards. The strong destruction is where the slope is steepest, near the equator, and that's by the hydroxyl in the equatorial atmosphere, about 3 kilometers up. And then the southern hemisphere is this waveform at the bottom, where it's mostly ocean, and there isn't much methane. And that's South Pole at the end there. And you can see the increase, and you can see what's going on in the methane budget. It's growing fast. And this is actually a map showing the same thing in a different way. The year along the bottom, and up and down is the sign of the latitude. So that's proportional to the area of the land. The Arctic is just that little bit at the top above about 0.9. The tropics are sort of big chunk in the center, and then the Antarctic is a bit at the bottom. The hot colors are strong growth, and the cool colors are decline. And up to about from 2000 to 2007, methane was in rough equilibrium. It grew some years, it declined other years. You can see the very hot year of 2003 on the left here. Some of you remember that year. And then the decline that followed afterwards because the methane blew away. Now, in 2007, something started happening, and methane has been growing almost continuously since. In the southern hemisphere, continuously. In the northern hemisphere, there's been some ups and downs, but basically it's continuously growing. And then in 2014, something extraordinary happened. The methane growth rate across the entire planet was some of the highest we've ever recorded. And that's continued. The biggest growth has been in the tropics, but there's actually been strong growth north of 30, between 30 and 60 mid-latitudes in the north as well. And we don't know why this is happening. Okay, what are the causes of the rise? It could be that the emissions are increasing, the tropical wetlands especially, and a lot of the tropical focus seems to be that. This is us running around tropical wetlands. It could be that the sinks are declining. Sorry, that says increasing destruction. It should say decreasing. I must have been hopeful last night. Decreasing destruction. And that actually has an isotopic sink that isotopic shift that drives the isotopes the same way. And there's quite a lot of evidence that the tropics are effectively expanding. So there's a lot going on in the tropics. And at the moment, we just don't know. We're trying to figure out from the isotopes what's going on. So we run around and measure isotopes of methane from smoke or from rice fields. Or those are actually Grace Mugabe's cows, of all things. They're volunteering to serve science. I'm not a supporter of Grace Mugabe, I'm afraid. But her cows are very helpful. So fires are pretty important. And this is a fire near my home in the Eastern Cape. And you can see how that just throws up material into the, initially 5,000 or 6,000 feet, but eventually that mixes quite widely. A lot of fires now, of course, are human lit. They're not lightning lit. We actually take the UK research aircraft to and fro in our project. This is us in Senegal, and we're flying over a fire there that was actually pretty scary because we flew far too low into it and bits of trees were hitting the cockpit. It was very scary indeed. My postdoc then rather stupidly said, let's go out to sea and get some fresh air, because we needed a background to compare with the fire sample. And the pilot said, oh sure, we went out, and we went out at 5,000 feet and 54321. I was watching him down, and I thought, okay, we'll get a sample. Oh no, 1,000 feet. 98765. It's going to stop at 500 feet. No. 54321. It's going to stop at 100 feet. No. 90, 80, 70, 60. Please stop. He stopped at 50 foot. Well, he didn't stop, but he flew a kilometre or so at 50 foot. And then I realised that humpback whales jumped to 8 metres. And were he a couple of feet wrong, we could be the first 4-engine jet ever brought down by a humpback whale. And we get a Darwin Award. But we didn't get it. But these maps here are the satellite maps of fires, and you can see just how much fire there is in Africa. Human lit, clearing crops. More pictures of fires. We've been doing the isotopes on them. You can figure out the isotope. Every emission has an isotopic signature, and then you can work out the budget just by adding up the isotopes. Now the destruction is this. This is the cleaner of the atmosphere. The bright, moist, tropical troposphere, which is where it's all cleaned up, because all these species are oxidized here by this wonderful hydroxyl. And now if hydroxyl is getting less, then there's problems, because then the pollutants will build up. Methane's not strictly a pollutant, but it's definitely doing bad things. But there are plenty of other pollutants as well which are hit by OH. Okay. Now this has consequences. This is a calculation by Martin Manning, who's a friend of mine in New Zealand. And he's been looking at the Paris Agreement. And the idea behind the Paris Agreement is that if we stick to it, we'll at least limit warming to something that society can just about tolerate. Whether the natural environment can tolerate that, who knows? But humans can probably sort of work their way through a limit if the warming's 1.5 degrees by the end of the century or something like that. But we're pretty close to those limits. Now, CO2 is the red circles, and you can see that we're sort of at the moment very roughly on track, mainly because of the financial crisis and the recessions. But great things are happening in CO2. Right now, China emits as much carbon dioxide as Europe and America together. India is closing in on equaling Europe, especially after Brexit. Chinese emissions over the last few years equal the entire British Empire's emissions through its total history. Yeah. The size of these emissions is immense. But there's a lot of good happening. For example, solar electricity is now becoming cheaper than coal, if only you can store it somehow. So it's undercutting coal terrifically. Whatever you think about fracking, that's also undercut coal. So coal is now in very serious trouble. And then as solar and wind come down and batteries get better, we're increasingly getting to the point where the hydrocarbon, the gas and the oil are going to get challenged as well. It's taking time, but I think the best thing we can possibly do right now is build better batteries. So that's CO2. N2O, which is largely forgotten but terribly important greenhouse gas. It comes from things like making nylon and also from agriculture. And everybody just ignores it. That's growing, and that's a problem. And then the green is the methane. Now, zero is compliance with Paris. So the stuff that's not compliant with the Paris objectives, that's the methane. And the more that grows, the tighter it puts the limits on the CO2 that you can emit and still keep to the Paris objectives. So you could argue that methane is now the big challenge to the Paris Agreement. We don't know why methane's growing. And a lot of it looks like warming feeding warming, like feedbacks. Whether it's a feedback through OH or feedback through more production from wetlands or from more cows in the tropics. And these are very hard things to deal with. You can argue about cows in industrial countries, but where are the cow superpowers? Obviously, India is the biggest one. But then you get to cow superpowers like Ethiopia, South Sudan. We're not used to thinking of South Sudan as a superpower. Comes to cow numbers, yeah. Okay. In methane in particular, we've got an awful lot of improvement in detection. We can do things. We can cut. We can't do very much with things like how many cows are there in India, but we can do an awful lot with stopping gas leaks, which actually is also profitable, thank goodness. So stopping gas leaks is very, very high on the agenda, I think. That's the easiest and simplest thing we can do. And that's also politically possible. But nobody really seems to have been asking these questions. The Queen went and asked a wonderful question of the London School of Economics when the financial crisis happened. Why did nobody notice it? And the answer is some people did probably notice this, but nobody was listened to. Yeah, you get treated as Cassandra. Yeah, if you ask about the big things, it's hard to tell. One of our big problems is that there's absolutely no support for long-term measurement. I've actually had a grant proposal rejected on the specific grounds that this smells like monitoring. We used to monitor up in the Spitsbergen. This was 15 years ago, looking for winter emissions of methane from the Russian gas fields. That was closed down by the European Union on the grounds that you could do it from satellites. But satellites do it with sunlight, and you're up in Spitsbergen in the winter, there ain't no sun. And also the satellite errors were 2 orders, 3 orders of magnitude bigger than us. and they couldn't measure isotopes. So monitoring is the real Cinderella. Now, we do have success there, a tremendous success. Right. The Montreal Protocol. This is the best thing we've done for the greenhouse, let alone for the chlorofluorocarbons. It saved the ozone. If we had not had the ozone treaty, by now, the amount of ultraviolet coming through in the tropics would be so serious it would be burning off leaves. Spring wheat crop in the prairies would probably be getting burnt. It's not just humans getting sunburn. It was saved. And the reason it was saved was I'm not a natural supporter of this particular person. There was a scientist who had a very good background in chemistry with a Nobel Prize winner teaching her. And she got interested, and I've been told that she actually read all the papers, understood the science properly, and her speech to the United Nations in 1989, I think, I can't remember, was one of the best speeches there's ever been on the climate problem, Margaret Thatcher. She deserved a Nobel Peace Prize for that. Because she went and told George Bush, you've got to do this. You'll notice that very recently Matt Rigby, who's actually in our Maui group, spotted that the Chinese are releasing CFCs again from Manchuria. And he used the A-gauge network, which is linked with us, just by running the winds backwards. So there is hope. We've got this. We can do it. There's pessimism, and the problem's terrific. There's optimism, though, that we can do it. The planet won't be what we grew up with. But the good thing about this problem is it brings us together. We can only solve it together. We can't solve it if we argue with each other. It's the sort of problem that makes humans collaborate. My wife's in Darwin College, and my favourite bit of the Darwin Garden comes from the Darwin family 100 and some years ago. Underneath Sir George Darwin's bedroom, he planted a vine and a fig tree. And anyone who knows Zechariah will know why he planted a vine and a fig tree. And they're intertwined. They're absolutely marvellous, and they're still there. So I will conclude by saying, yes, we can hope. And maybe this is the sort of problem that does bring us together. It's a very, very tough problem. But if we solve it, we get somewhere. Okay.
Thank you very much, Euan, for taking us through the science of that and actually worrying us, but I hope giving us some hope at the end. We've run rather over time, but I'll take just one question, and we'll take it there, and then there is an opportunity, as I say, to stay afterwards to discuss further.
Hello, my question relates to, I think, the law of Adam.
Yes.
And to the urgency of our predicament, and to, I want to know if I invite you to make any comments you feel might be worthwhile on how the world of science, in inverted commas, engages with a culture characterized by, in the American, a well-known phrase is saying, in the American accent, which I'm not too good at copying, it's just a money-making industry.
What, is science a money-making industry, or?
It's just a money-making industry.
Okay. Well,
also that relates to Paris.
Just a quick comment on that.
Yeah, very quick comment. First of all, I very, very specifically do not take any money from industry. So my funding is entirely from NERC, the European Union, and the United Nations. Yeah. I owned Bays recently for a small project. But, yes, the oil industry is a money-making industry. The cow industry is a money-making industry. It actually means human beings. The cows of India, that's a religion. We've got to solve these. It's very, very tough, and they're huge vested interests. But we've got to get them together.
Okay. I think we probably need to draw to a close. I said we would finish at 2 o'clock, but there's an opportunity to stay around for another cup of tea afterwards and discuss things further. But can you join me in thanking you and from